Hello, one more example. F of x equals x to the power 5 over 3 minus 5x to the power 2 over 3. Powers. Again, we use the same strategy to graph. First, getting the domain. It's all real numbers because those are cube roots. Cube roots are defined everywhere. This means we have, for the second point, no discontinuities. Directly, we look at what happens at the limit at plus and minus infinity of the function. Anything with powers behaves like the highest power. And this, at plus infinity, 5 over, raise it to the power 5, then cube root it, the answer would be plus infinity. Anything negative infinity, raise it to the power of 5, it will stay negative, then cube root it, it will be negative as well, infinity. So, and of course we have no oblique asymptote, nothing. Now we look at the derivative. 5 over 3 x to the power 5 over 3 minus 3 over 3 minus 1, which is 2 over 3, minus 10 over 3 x to the power 2 over 3 minus 1, it is minus 1 over 3. We said that this is not convenient, it has to be in simplest form, meaning that you drop this power down so that the next step would be taking a common denominator. You get 5 x to the power 2 over 3 times x to the power 1 over 3 is x to the power 3 over 3, which is x to the power 1, which is x, minus 10. This is 5x minus 10 over 3x to the power 1 over 3. This is f prime of x. I'll directly do f double prime of x, but I will be very wise. See, if I'm wise, I save myself some problems. See, I don't use this answer to get the second derivative. I use this answer to get the second derivative. Much easier. 5 over 3 times 2 over 3, 10 over 9. X to the power 10 over 3 minus 1 is minus 1 over 3. Minus 10 over 3 times minus 1 over 3 is plus 10 over 9. X to the power minus 1 over 3 minus 1 is minus 4 over 3. Equal 10 over 9 common. You're left with 1 over x plus 1 over x to the power 4 over 3. You take a common denominator. What's common between 1 over 3 and 4 over 3? 4 over 3. What do you multiply x to the power 1 over 3 with to get x to the power 4 over 3? X to the power 1. So it's x plus 1. Think about it. In order to take a common denominator, I ask myself, is there a number? I multiply it up and down so that they become the same. When this is any multiple actually of 1 over 3, if it was 4 over 3, 5 over 3, 7 over 3, anything, then how do you multiply this? Or any two powers actually, can we calculate them from each other? Yes, because this one, you multiply it by 4 over 3 minus 1 over 3, which is 3 over 3. When you multiply it by 3 over 3, you add the powers. 1 over 3 times 3 over 3, 4 over 3. So when you do x to the power 3 over 3, x to the power 3 over 3 up and down, it becomes the same denominator. And 3 over 3 is what? X to the power 1 plus 1. So this is my first derivative and my second derivative. Now I can answer simple questions. When is f prime equal to 0? When the numerator is 0. So when 5x is 10, so when x is equal to 2. Is the derivative ever undefined? It's undefined when the denominator is 0. This means this is 0, so x is equal to 0. Remember, the domain is all real numbers. So that's why the derivative is undefined at 0, not the function itself. And now let's move to the second derivative. What are the zeros of the second derivative? The numerator has to be 0. So x equals minus 1. When is the second derivative undefined? Again, when the denominator is 0, so when x is equal to 0 as well. So now we can create our table of variation. X runs from minus infinity to infinity. Minus 1, 0, and 2 are the points that we just gathered. F prime of x, who is important? 0 and 2. But the 0 is an undefined value, so we cross it. The 2 is a 0, so we put a 0. It's an XO. X because it's undefined, O because it is defined. It's not like what I did in previous examples where I scratched the whole thing. I scratched the whole thing when it's not part of the domain. Here the 0 is part of the domain, but it's only causing a problem for f prime. So now before 0, I choose minus 1. I substitute it here. I get minus 5 minus 10 minus 15, negative. Cube root of minus 1, negative. Negative over negative, positive. Between 0 and 2, I choose 1. I get minus 5 over 3, negative. Between 2 and above, I choose, for example, 8, because I know it's cube root. 5 times 8, 40, minus 10, 30, over 6, positive. Do you see this? Now I move to f double prime. What values are important to f double prime? Minus 1 and 0. Minus 1 is a 0 of f double prime, whereas 0 is an x value, is an undefined value of f double prime. I now look at this. This is always positive. I don't need to worry about it because it's x to the power 4. So it's raised to the power 4, so it's always positive. I only need to worry about x plus 1. Before, at minus 2, this will be negative, because minus 2 plus 1 negative. Between minus 1 and 0, like minus half, it will be positive. And bigger than 0, like 1, it will be positive as well. All right, so now we drop all the lines. See, I don't scratch here, I don't write an X or anything, because what is this about? This is about F. For F, everything is defined, nothing is scratched out. Here I have increasing concave down, increasing concave up, decreasing concave up, increasing concave up. So increasing concave down, increasing concave up, decreasing concave up, and increasing concave up. If you don't have them in your mind directly, what do you draw? You draw the smiling face and the frowny face, and then you group them. Now I can do a lot of conclusions. All right, what are those conclusions? I want you to learn to write those conclusions every single time. F is increasing, decreasing, local max if it exists, local min if it exists. F is concave up, F is concave down, and F has an inflection point. We have to deduce those from the table of variation. So let's look. It's increasing from minus infinity to 0 and 2 to infinity. I will write it, minus infinity to 0 and 2 to infinity. It's decreasing from 0 to 2. It's decreasing from 0 to 2. It has, anytime it changes monotonicity like this, it was increasing, it started to decrease. What do we have here? A local max, where at x equals 0, we need to find the y as f of 0. Do we have, what do we have? Another extreme value. It was decreasing, it started to increase. So what do we have? A local minimum when x equals to 2, and we find y which is equal to f of 2. The function is concave up from minus 1 to 0 and from 0 to infinity. Minus 1 to 0 and from 0 to infinity. It's concave down from minus infinity to minus 1. Does it have an inflection point? We have an inflection point when we change concavity from minus to plus, so we have only one inflection point here. It is at x equals minus 1, and we need to find the y value, which is f at minus 1. You see the conclusion? Increasing, decreasing intervals, those are intervals. Those are our points. When x is equal to 0, y is equal to 0. When x is equal to 2, y is equal to 2 to the power 5 over 3. We go and substitute in the original equation now. Minus 2 to the power minus 5 multiplied by 2 to the power 2 over 3. The answer is minus 4.76. So تقريبا 8. And then here at minus 1, the answer is minus 1, minus 5, minus 6. Because here it's squared, so minus 1, minus 5, minus 6. All right, so those are the conclusions. Okay, now intercepts. Y-intercept when x equals 0, y equals 0. So we only cut the y-axis at the point 0, 0. The x-intercept when y equals to 0, this means that x to the power 5 over 3 minus 5x to the power 2 over 3 is equal to 0. To be able to solve this, we always need to think outside the box. So that's why we learn together the first time, then we do it on our own. So in order to be able to solve this, what I have to do is I have to take x2 over 3 common factor. What I have left is x minus 5 here. Because see, when I take x2 over 3 to the power common factor from this one, as if I subtracted from the power 2 over 3, 5 over 3 minus 2 over 3, 3 over 3, which is 1. When is this equal to 0? When x equals 0 or when x equals 5. So we have two x-intercept. 0, 0 by default, and 5, 0 is the second one. All right, so now let's look at the graph, which is the last thing that we care about. The points are 0, 0 is my local max, 2 minus 4.8 minus 1 minus 6 0, 0, and the intercepts are 0, 0 and 5, 0. Now let me copy the table of variation. So in the first part, we are decreasing concave. So we are increasing concave down. زرقنا حالنا. Increasing concave down. Then increasing concave up. Then decreasing concave up, then increasing concave up, then decreasing concave up, then increasing concave up. Do you see this? Do you see this point over here? It's a cusp. It's where the derivative does not exist. So we were increasing normally, we inflected here. So it was an inflection point. We increased, and then we decreased. See, this caused a cusp, and this shows from having a derivative that does not exist. See, nice how things boil down. So this is another example of a graph where we have powers. Thank you.